Okay, now let's go to example 3 and stick with that same example but change it up a little bit. I'm still starting here with the same pressure and the same temperature, but I'm going to go down isothermally to some final volume V prime. So since it's isothermal, we're going to say T prime, the temperature at that corner, is the same as its initial temperature, right? Then I'm going to go back isobarically, then I'm going to go back adiabatically, right? So instead of going down isothermally and then cutting down isovolumically, right, this way, I'm letting it go longer. So is this going to be more efficient or less efficient? And let's see what the differences are, right? So let's calculate what V prime has to be. Since it's isothermal, we can say P prime and V prime over T prime is equal to P initial, V initial over T initial. And then the T initial and the T prime are the same, right? So then we can say P prime is equal to 0.2 atmosphere. V prime we don't know. T initial is 1 atmosphere. And then V initial is going to be 0.4894. And then we can calculate V prime that way, right? Okay, then we can do all of the other calculations, the heat and delta E and the W, right? Okay, so then we can say here Q1 is going to equal delta E1 plus the work done by gas in stage 1. Delta E1 is going to be 0, right? Because it's isothermal, right? So then we have here Q1, and then the work done, this is an isothermal process, so it's going to be nRT ln V final over V initial, right? 20 times 8.314 times the temperature, which is the 298.15, so this is also going to be 298.15, right? So 298.15 ln of, and then V final is going to be the 2.447 divided by V initial, 0.4894, right? So then we're going to calculate here L1. So Q1 equals W1. So that's how much heat is coming into the gas. So notice that that is a lot less heat than the heat coming in during the isobaric process, right? So then you're going to have here, okay, so then that's 79.790, right, kilojoules. And then that's going to equal to the work done by the gas, which is also going to be that. So this is Q1, and then the W1, 79.790 kilojoules, right? Then we can find out for the second stage what's going on, okay? Okay, Q2 is going to equal W2 plus delta E2, right? Well, we can calculate each one separately because the delta E2 is going to be equal to 5 halves nR delta T, 5 halves 28.314. Okay, the temperature that it has here, remember, was 188.25 Kelvin, right? At the end of the adiabatic process, so that's still the same answer, right? So my T final is going to be 188.25 minus the initial temperature, which is 298.15, right? So then I'm going to subtract those and then multiply it by that. Well, if you realize that it's actually the same as this answer, the 45.696, just again within rounding error. So because the change in temperature from 188 back up to 298, it's going to give you the W3 and delta E3, 45.696. Here the temperature is the same as 298, right? So then the loss in internal energy should be the same as the gain in internal energy there. So I'm just basically going to round that to 45.696. Again, it's basically rounding error. So then here I have delta E3 is negative 45.696. So the pressure is 0.2 atmospheres, right? 0.2 times 1.013 times 10 to the 5th pascals. So that's 0.2 atmosphere changes to the units of pascals. Delta V is going to be the final volume, which is this volume here, 1.545 minus the initial volume, which is the 2.447. Okay, so W2 plus delta E2, so negative 18.275 right? Plus delta E2, which is going to be plus negative 45.696. So basically you're adding the two numbers because they're both negative. So 45.696 plus 18.275. Then it's going to be negative 63.971. Right, so that's going to be Q2. So that's we can shade that in. And we can say, okay, heat is coming out of the system. Q2, negative 63.971 kilojoules. Right, which the negative means that it's coming out of the system. Right, so then I can check the totals and see if I'm good, and then I can do the efficiency of the engine. Okay, so the two cancel and it comes back to the original state. So we can see that that's working, right? So then you're going to have here Q total. Q1 was equal to 79.790 plus Q2 was equal to negative 63.971, right? And then this one was a Q2, and then Q3 was 0. So then the total net heat coming into the system is 79.79 minus 63.971. So that's going to equal 15.819 kilojoules. That's the total heat coming into the system, right? And including the heat coming out. So then you have here the work total is going to equal the work in stage 1, 79.790, plus the work in stage 2, negative 18.275, plus negative 18.275, and then you're going to have plus, and then the work in stage 3, negative 45.696. Okay, so that's the total work done by the gas, 79.790 minus 18.275 minus 45.696. 15.819 kilojoules. Just amazing, right? How it always comes out. So 15 net total heat coming in and out of the system. The gas is doing 15 kilojoules of work. So let's compare this to the first case. The first case, the graph looked like this. Which one was the area under the graph more? This one looks like it's more because the other one is coming and it's just coming straight down, right? So you're getting rid of this portion of the area. The first one is this much work. This one includes more work, right? I think the first one, the work done by the gas was 11 kilojoules, whereas in this case, the work done by the gas was 15. So this extra area was about 4 kilojoules of work, right, that the gas did, right? But the total heat that I had to put in is also probably more, right? What was the net heat? 15.81, no, the total heat, the heat that I had to put in was 79, right? So the efficiency is going to be the work done by the gas, work by gas, divided by the heat in. So 100%, right? So the work done by the gas was 15.819, right? And then the heat in was 79.79. So %19.826%. Very close. What was the other one? The first example, the efficiency was, I believe the efficiency, the work done by the gas was 11.307 divided by 56.993. So in the first example, the gas did less work, but it required less heat of me to get the gas to do that work, right? So 11.307 divided by 56.993 it was 19.839. So this one is slightly more efficient than this, but they're very, very close. This one requires more heat for me to get the gas to do the work, and then the gas does more work. And then this one requires less heat, but the gas does less work. They're very, very close, with this one being a little bit more efficient. And I think where that comes in is the fact that you have an isobaric process also. Isobaric process tends to make the system a little bit less efficient because you're trying to keep the pressure at being constant. By making the pressure being constant, you're dumping a lot of heat here, 63.971 kilojoules, right? And so you're not getting as much efficiency out of it, but they're very, very close, so we can't argue that there's too much difference between the two. But in the second example, where it was straightforward with isobaric process, you can tell in that case it was way less efficient, about 16%, about 3-4% less efficient, right? Okay, so now you can see the three examples, how they interrelate with each other, and then how to also check to see if the totals match, and how to calculate the efficiency of the engine, okay? Thank you very much.